If I wanted to construct a kite, how could I do it? You know, like get some string. No. Dadgummit. 30 minutes of me just trying to do this. Okay. Everybody take a minute to draw a kite on your paper. Whatever paper you got, draw a little kite. Draw a little kite. You don't have to put a design on it unless you want to. Put a little tail on it. Alright, so let me follow up. Can anyone tell me, so did you observe yourself while you did it? Where did you start exactly? Anybody want to share with me how did you start making the kite? What did you draw first? Oh good, you drew the top of it, yes? Because what's supposed to be true about a kite? These two have to be same length, and we're doing it by hand, so it's okay if they're not perfect. In fact, you could tell this guy's a little longer, so let me just do that a little bit. And then you can just go crazy with the other side, really, right? You just got to make sure that it's sort of symmetric with the other vertex, because these two have to be the same length, yes? So I'm pretty sure probably nobody did this, but that's a kite, because these two are the same length and these two are the same length. Okay. So we all know what a parallelogram is. So what kind of things? I'm kind of giving away one of the answers in the quiz, but I'm okay with it apparently. What kind of things? What's the only kind of shape that could go in the middle that would be both a kite and a parallelogram? Because if you think about it, a parallelogram, what's true about a parallelogram? Parallelogram, what's true about a... Yes, he's got two pairs of parallel sides, yes? So opposite sides must be parallel, they don't have to be. So this is a kite, this is a parallelogram. You just kind of do offset things here. Oh God, this has had a rough day. Okay. Parallelogram. Okay. Obviously, why is this not a kite? Why is the parallelogram that I've drawn not a kite? Because this side is not the same length as that side. So if I want to make my parallelogram into a kite, yes? Then I'm going to do what? I'm going to smoosh it until the side is the same length as that. And then what officially, it's still a parallelogram, but what is it more specifically? A rhombus, yeah. You could also think about the kite. If I wanted to make this into a parallelogram, I'd have to push this up until this side becomes parallel to that side, and I get sort of the same idea happening. Yes? Maybe? No? Screw you, Jeff. Only a math guy can make kites evil? Okay. All right. Okay, so if there's no other questions from the quiz, that was sort of a question I asked myself. I want to show you, let's start off with watching some young people. I don't think I've shown you this series of videos yet. Tell me if I did. I don't care. I'm going to fully embrace my old man brain. So if I already showed you this, just let me know. Oh shit, I better stop this guy. Okay for me to say shit, but I can't do a copyright strike. Okay. So, what we're going to focus on today, you guys have a piece of paper? Everybody have a piece of paper? So very quickly, I can't remember if I pointed this out already. Probably at some point, you guys, in the last semester of this. See the ceiling? You guys see that ceiling up there? It's always nice to know it's up there. If it wasn't, we'd be getting ready to. You guys see how the ceiling, if I consider it to be a plane, is covered by rectangular shapes. So if I use a rectangular shape repeated, I can completely cover the plane of the ceiling. Yes? We talked a little bit about this already. If you took a little piece of your paper and you try to cover it with triangular shapes, could you? So like if you just take a corner of your paper, could you cover this with triangular shapes? All right, try. And I mean a repeated triangular shape. So like the same shape. You don't have to give yourself, you can kind of open it up a little bit. So like if you do this, and then if you repeat that shape but go like this, yes, that's kind of like the standard way to do it. Do you guys see if you use an equilateral triangle, you can very easily cover the plane of the paper, yes? Okay. What shape did I just make all together if I fuse these together? Trapezoid. If I put one more equilateral triangle, what shape is that? So if I figure out a shape that can cover a plane, then any shape that those shapes fuse together to become will also cover the plane. Does that make sense? I love you guys. Do you all agree that I could cover the whole paper if I was really bored? Which some of you guys might be doing right now. If I was really bored, I could just take an equilateral triangle and just cover the whole paper with it. You guys agree? Yeah. Okay. And if you imagine the paper extending forever, you could just continue forever. Okay. Now, at the edges, you couldn't perfectly do it because I don't have a straight edge this way. But if I just let it go forever, it would work. Okay. If you try to now, therefore, a parallelogram made out of those shapes must also work, because it's just those shapes in packets now, yes? So if I continue a couple more times, what's this here? Trapezoid. And what's this here? Another trapezoid. So one level of covering a plane with a repeated shape is realizing that the shapes that I pick could make other shapes that would work. So other bigger shapes, yes? Okay, I love you guys so much. Have you guys heard of, well, okay, before I go there, and actually I know you have, because I'm pretty sure I put his stuff on one of my things here, my homework sheet or my syllabus, I can't remember which one. If you try to cover with circles, what's immediately an issue? They can't come together. And if I try to use even smaller circles to help me, there's always going to be space, yes? Let me see if I want to freak you guys out. I would have to get infinitesimally small to be able to fill it all in. So I can't, with a repeated circle, I can't fill a plane. I can't cover it. And what we call these, if I manage to cover a plane with a repeated shape, it's called a tessellation. And in fact, maybe more tessellation, Jeff. Let me be more less specific. I don't have to use the same shape. I could use several shapes to cover a plane. So let me show you one nifty example. Got a little ahead of myself. I do that often. Here. Or several nifty examples. Let's focus on one of them. So anything jump out at you? What shapes do you see? Triangles. Yes, because how many sides do you see? 6. And do you see, can anyone see that the hexagonal shape is also a bunch of triangles put together, of course? Just like we did when we had the fraction shapes last semester. That's exactly what this really is. So do you see the hexagonal shape here also? Jeff, you could do it there. Right there, there's a hexagonal shape, so it's just cut into these triangles. So to be really honest, this first one's not very impressive because all they did was, every now and again, they just colored this in red. Do you guys see what I'm saying? So it really is triangles, just some of them they grouped together. I have no idea why this one is pink though, so don't ask. Over here, same idea, really. Do you see how it's just hexagonal shapes repeated? This one's a little more impressive. Now this one's a little weird. What would I put here, of course? That dude. Now let me see. Can you guys see? I'm as zoomed in as it can be. This is not easy to see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 sides to this, yes? How many different shapes are we using here? We're using this guy, which we'll talk about soon. We're using squares, we're using triangles. You guys, that's the idea. So I could either use a repeated shape or several different shapes that are still repeated to try to cover the plane. That's what's called a tessellation. Let me stop for a minute. All the tessellations so far we've seen are created by multi-sided figures. Yes? In fact, to be more specific, can anyone tell me, for example, that shape right there, can anyone name that shape? Is it a quadrilateral? How many sides is that? So what's the name of the shape? No. What's the place in DC where military people? Pentagon. Now the Pentagon has your standard pentagon shape. It's like perfect, yes? This one is a pentagon because it's got 5 sides, but it's not what we call a regular pentagon. A regular pentagon, all the sides would be the same length and all the angles inside would be the same length. How are we doing? So for example, an equilateral triangle is an example of a regular polygon with 3 sides. All the sides are the same length, all the angles are the same length. Let me stop for a minute. Now, I am a math teacher. I'm used to people being horribly bored of what I'm saying. Man, I don't know. We'll be all right. We're going to get there. We're going to make it. Okay. So, coming back. So, I want to start there because I want you to realize there's some really cool artistic stuff you could do with this. In fact, let me go ahead and show you this. Some of you guys saw me searching for this earlier, but let's see, we don't need you anymore. We'll get there. Here we go. No, stop. Go away. Image, thank you. Where did it open? Here? Yes. Has anyone ever seen this before? Okay, nobody's ever seen it before. Can you guys see what's going on here? Especially if you look right in the middle of it. Do you guys see how it's the same shape, just colored differently? Yes? And if I actually took this and kept going in both directions, wouldn't this shape cover the plane of the whiteboard here? You guys with me? That is a much more interesting shape than a rectangle. Yes? It's even more interesting than a triangle. You know, it's what the shit. So the artist who did this, I've talked about him before. His name was M.C. Escher, and he was the idea man behind the Labyrinth movie at the end when he's doing the stairs. So if you ever seen the movie Labyrinth, when he's walking around the stairs and going upside down and stuff, that's based on one of Escher's works. That is simply cool. I don't know if anybody agrees with it. You guys, you don't have to. You can hate that if you want to. But that's just stupid cool, especially the way he takes and kind of morphs the shape into the shape of the fields down here. Yes? It's just neat. Okay. Just to show you a couple more. Here's one with lizards. No, Jeff. Open image. There we go, buddy. Can you guys see that one? Lizards. Yes? Lizards. Okay. So Escher was fascinated by what other shapes could possibly be used. No, Jeff, you're never going to learn. To accomplish this besides boring old rectangles and triangles and so forth. Yes? Okay. So here's a little bit, I'm not going to, that's coming up later. Here's a little bit about the math. Did you, no, you didn't. Okay, real quick. Standard, reliable, will work, boring. Start to play with the picture, yes? Make a change, repeat the change. Now I have these nifty little puzzle pieces. Do you guys see how this is a dude and he fits right into the next guy? Yes? Yeah, it gets a little weird, but we're gonna be okay. And then you just kind of keep doing that. You keep changing the side and making the same change on the other side, yes? This is one very standard way to make non-standard shapes that would still work. And that's basically what Escher did a lot of. He kind of like pioneered this thought process. Okay. I don't think, no, they don't get too much more into it. Okay. So that's Escher, that's his work about tessellating a plane. Okay. So, that's the idea of a tessellation. And they're composed of potentially anything that works. But the most basic ones are composed of polygons. So let's first figure out what the hell is a polygon. So first off, this is a curve. That's amazing. More specifically, it's a simple curve. So what is it about it that makes it a simple curve? Well, to not be a simple curve, it has to kind of like loop on itself. This is not simple curve. Okay, that's exciting. If I have a simple curve that is composed, so real quick, is this a simple curve? Yes, I love it. So what's weird is the word curve makes it seem as if it's got to be curvy, but no, it just has to not come back on itself. So that is a simple curve composed of line segments, if you want to get really specific. Let me stop for a minute. So what do you think simple, so this is a simple curve, this is also a simple curve. What do you think simple closed curve means? No, wait. So take a minute. Draw a simple closed curve. So one thing you could do, did anyone draw a circle? That's your most basic standard simple closed curve. Yes. But anything like this is a simple closed curve. Yeah. That is a simple closed curve. Why? It doesn't intersect itself. It doesn't make a loop inside or outside. It doesn't loop. It doesn't intersect itself. And it actually closes. It meets itself. Stop for a minute. So all a polygon is, it is a simple closed curve composed of line segments. Holy shit, let me write that down. So a polygon is a simple closed curve composed of line segments. So here is a polygon. That is a polygon. Pretend like all my sides are straight. I have trouble being straight, apparently. You guys with me? Now, that's not a standard shape, is it? That's not standard. It's not like a regular polygon. But that is officially a polygon. Okay, okay. If I put on the extra stipulation that all the side lengths and the angles are congruent, let me see if I can do this. That'd be so cool if I could. Oh, you almost did it, Jeff. All right, for me, that's really good, which is pathetic, but we're gonna be okay. So this is my attempt at drawing a regular polygon. So 1, 2, 3, 4, 5, 6, 7, 8. Pretend like this is shorter, okay? So a regular polygon, you missed this letter there. Regular polygon has congruent sides and congruent angles. So all the angles would be the same. So of course, like I said, you've got this is now let me show you the convention. The official name for this is a triangle. The extra official name for this, are you ready? So poly, real quick, do you guys remember what poly means? Polynomial, polyamorous, polygon. Poly means what? Many. So if I want to be specific, I could call this a three-gon. So polygon is multi-sided. Three-gon is three-sided. That's kind of silly on one level, right? And we're not suddenly it's not a triangle anymore. Of course it's a triangle. Every single three-gon is a triangle, yes? That's my attempt at a regular three-gon, which has got what very specific name? If it's a regular three-gon, what's the very specific name? Regular three-gon. Regular means all the sides and the angles are the same. So what kind of triangle? Equilateral, I like it. Cool. Okay, how we doing so far? Nothing too crazy. Nothing too crazy. Then you got your, what do you think a regular four-gon would be? No way. Okay. Square, aka square. And then your regular five-gon is kind of like your standard pentagon. And one way to do a pentagon is to make the top like a triangle shape, and then you make your little base. Oh my God, this is pathetic. That's a little too tall. This poor little guy. But if we all pretend that all the sides are the same length, which obviously it isn't, and all the angles are the same measure, this would be a regular five-gon, also known as a regular pentagon. Now, very quickly, rectangle is a four-gon. Is that cool? That is a foregone conclusion. Good stuff. So, rectangle is a four-gon. A regular four-gon we also call a square. Is this cool? So the word regular just means everything's congruent. Pentagon, we don't have like pentagons and then something else like we have rectangles and then squares. It's either just a pentagon or it's a regular pentagon. You guys see what I mean? We have a shortcut way to say regular four-gon. We just call it a square. We don't have a shortcut way to say regular pentagon. You just say regular pentagon. And then you can continue until you go a little insane. And just to show you, so we don't go too insane. And by the way, before I forget, the root of this is penta. And of course, gon means side. So penta is the Greek for five. So almost all of our names are taken from Greek. Some of them are taken from Latin. I'm not going to suddenly change this into a Greek or Latin course, so don't freak out. I do want you to memorize some of these. So at least you should know up until 6 or 7 sided. Let's say 7. So 5-sided is a pentagon. What's 6-sided? Hexagon. 11. Does anyone know what 7-sided is? This one's definitely not. Maybe I won't make you memorize this, but 7-sided. Oh, okay. All right, this is perfect. The official name for a 7-sided figure is a heptagon. This is a very interesting story. I don't remember what year it was, but there was a group of elementary school teachers who decided to rename a heptagon into a septagon. And this leads to a very interesting history lesson. And you're all like, what class am I in? Do you guys know why September is called September? Sept is 7, but September is the 9th month, yes? You guys kind of with me? So very quickly, Julius Augustus, I think. Yes, Julius Augustus. What 2 months does his name sound like? Julius Augustus. So of course, when he was in charge, he put 2 months into the calendar. He said, well, obviously I'm amazing, so let's take July and August because of me. We'll just stick those in there. And September's like, oh shit, okay, all right. You guys, I don't really agree, you guys. Anyway, that's all side note. You don't have to remember all that. But septa is 7. So the elementary school teachers thought this might be easier for students to remember, and then of course that's not generally good because heptagon is the actual official name. But I like that somebody's actually learned septagon. It's a very interesting side note. And of course my brain keeps saying this Decepticon, which is not good because it just reinforces how much of a geek I am. Okay. You don't have to know the whole story about septa and all that kind of stuff. And of course, since it's Latin, I think it's septum. But that's, again, don't worry about it. It's like carpe noctem. Seize the night. How about, all right, you guys don't have to remember, you guys should all know 8-sided. I think there's been, do you guys know 8-sided figures? Octagon. So I think that makes sense in a few different ways, because what do you think when you hear octagon? What animal? Octopus, okay. What about 9-sided figure? All right, this one's called a nonagon. Okay. And then of course a 10-sided figure. Some of you guys might know a 10-sided figure. Decagon, sort of like deci for decimal, based on tenths, deca. Okay. I like it. So I only need you to memorize up through 6-sided, up through hexagon. Okay. Most of you should pretty much have that already. I might add some bonus stuff about higher level stuff. So let me flash this up here. That didn't sound right, but we'll be okay. You don't have to write all this down, okay? Am I recording? I think I am. Yeah. So let's see if any of these sound familiar. Now, one lesser named name for quadrilateral is a tetragon. I'm not going to worry about tetragon. Then you got your pentagon, hexagon, heptagon, octagon, nonagon. It's also called an enneagon, but let's not worry about that. Decagon. Now this one's definitely weird. This one is one I always forget. So I didn't even remember it until I just looked at it now. Hendecagon. Hendecagon. There it is. Dodecagon, we kind of know. I'm not going to read all these. Look at this one. Supercalifragilistic. Okay. And then you get up to thousands, sided figure. Of course it's a chiliagon. Why not? Anyway, sorry. So I just want, you don't have to memorize this shit. You guys with me? Do not copy this stuff down. It's just kind of neat on one level to see what seems to be a part of this word. Hepta, and of course that relates to 7-sided. This is 17, so this is like hepta plus deca. So you can see their naming convention in a few places, yes? Okay, I love it. I love it. I love it. Okay. You only have to know up to 6. Yes, up to 6. There it is. All right, now, before we get back to tessellations, I wanted to open with tessellations because normally that's the more interesting part. So I'm really sorry I already put you to sleep with that already. But now we're going to get to the less interesting part. This is sort of interesting. If I have, what's this? How would you classify this? Quadrilateral. How else could you classify this? Trapezoid, not quite, yes. It's not quite. Well, I can see how you might think, but see how nothing's really parallel. See that? Quadrilateral, or what did we learn today? The less interesting name. Fourgon. Yes? Fourgon conclusion. Sorry. And what's this do? So this is a fourgon, and this is a... Yeah, it's a pentagon. I love it. And more generally also referred to as a fivegon. Is this a regular pentagon? How can you tell very quickly that it ain't? Doesn't it look like a pentagon? It's kind of like doing like this? No? Is it just me? All right. Now, does anyone know what we call any of these points here? What do we call it on a parabola, the turning point? The vertex. Yeah, so each one of these is called a vertex. Okay, I love you guys. Can you copy the pentagon on your paper? Doesn't have to be perfect, just want a pentagon. I don't want to waste paper and print all these out for you. I figured we could all draw. Anytime you want to, you can have your kit with you, use your protractor for a straight edge. But it's not that important here. I just need a 5-sided figure. So, you guys are going to do in a minute what I'm about to do with the foregone conclusion here. I can't stop saying that, I'm sorry. If I pick one vertex, you guys are going to do what I'm doing. I'm doing it with the easier picture because I'm the teacher, I get to pick out. I pick one vertex, and I'm going to make every triangle I can by connecting that vertex with the other vertices. What's the only way I can make a triangle by connecting this to other vertices is like this, yes? Do you agree? How many triangles did I just make? 2. Let me see if you guys are, let's see if we can power through this little proof. It's not really going to be a proof. I'm not going to get that deep. How many, and what do all the angles in a triangle add up to be? 180. So you guys should basically already know this. So this angle, I'm going to call it A, plus this angle is 180, yes? And this angle, plus this angle, add up to be 180. So what are all the angles, the 4 angles that are at each vertex, what do they add up to be in any foregone? 360. Which is 2 180s. Do you see why it's 2 180s? Because it's 2 freaking triangles, yes? How many sides were there? 4. How many triangles was I able to make? 2. You guys do the exact same thing on the pentagon. So just remind you guys, pick a vertex. Make all the triangles you can by connecting that vertex with the others. Now, obviously, one that's straight across from it doesn't make a vertex. That's a stupid side, so that doesn't count. So give it a try. Pick any vertex you want and just make as many triangles as you can by connecting that vertex to the other vertices. If you're not sure what I'm asking you, put a little face on them and make them Mr. Fivegon if you want to, but it shouldn't be too crazy. Sort of like this is, maybe know who this is. No, that's Bill. No, nobody knows Bill. Okay, there it is. Bill's side. All right. So I'm gonna pick. I don't care. What do you guys want me to pick? 1, 2, 3, 4, 5. Which one? 1. Okay. So this doesn't count. So here's. I can do that. Do that, and this doesn't count. Yes, so how many triangles did I make? 3. How many sides were there? How many sides are there in the original? 5. So there are 4 sides, and I made 2 triangles. 5 sides, I made 3 triangles. Interesting. So how many total degrees are in this? Each triangle has 180, and I have how many of them? So 3 times 180, 540. Yes. Yes. Just to remind you guys, 3 times 100 is 300, 3 times 80 is 240, 300 and 240 is 540. Right, don't forget all the shit we learned last semester actually should help you out too, not just your future students. Okay. All right. Made this color too dark. It's going to be okay. Look at this guy. All right, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes? How many triangles do you think I'm going to be able to make? What's the pattern seem to be? Yeah, I'm probably going to be able to make 10, right? And if I do it very quickly, 1, 2, oh, good Lord, Jeff. Look at that. 3, 4, no, Jeff, fine. All right, so you would make, I don't know why, I made the color too dark, I didn't get lost in the middle. You could make 10, so it's always, always, always. If it's an n-gon, I can draw n minus 2 triangles. Now, what's the point of this? Well, what's the point of anything? I don't know, guys. Yes? So this had 12 sides, so I could draw 10 triangles. So what would the total angle measure inside be then? $1,800 degrees, yes? For every triangle, it would be 180 degrees. I have 10 of them, so I have 1,800 degrees. Let me stop for a minute. Okay. So in general, for any n-gon, what would I do next? I know I can make n minus 2 triangles, so how would I figure out the total degree measure? Do it again? Yeah, n minus 2 times 180. Let's check this out. Let's check it out. 3-gon is also called a triangle. Sides are 3. 3 minus 2 is 1 times 180 is 180 degrees. This is a triangle. I have 180 degrees. Yes. Could you have a 2-gon? Imagine, try and make a 2-gon. So it'll be one line and then only one more line. So wouldn't you have to kind of like go back on yourself? Wouldn't they have no degrees? Because it never opened? Isn't that what I get? Now, if you try to do a 1-gon, forget it. I mean, that gets way too weird. I would have negative degrees officially, but it goes down to at least 2. 2 makes sense. And forever up. So if I had a 358-sided figure, I could figure out how many total degrees there would be inside. Now, real quick. Yeah. I can go ahead and get ahead of myself a little bit. Yeah, we can do it. If I have a triangle, an equilateral triangle, so this would be a regular 3-gon. It's another name for an equilateral triangle. We already know there's 180 degrees total. How do I figure out how much each angle gets? How big is each angle then? All the angles are the same in an equilateral triangle, and it's 180 total degrees to go around. How big is each angle? Some of you guys should just know this. How big is the angles in an equilateral triangle? 60, because it's 180 divided by 3, yes? Do you guys agree that it makes sense that there's 3 angles, because there's an angle across from every side? So I always think of it as a mouth opening, and the side is a stick in the mouth, yes? Okay, we stop for a minute. Hey. So it's just kind of wandering around seeing what things are going on. Oh, still us. Sorry. So, if I come back to this, well, not that. If I had a regular pentagon, yeah, here we go. I got a regular pentagon right here. Let me see if I can. Yes, money. Okay, that's pretty good. Okay. So regular pentagon. Remind me, how do I figure out how many total degrees total?
N minus 2.
Good. N minus 2 times 180. So that was 540, yes. How would I figure out how big each angle is? Yes, because I would have 1, 2, 3, 4, 5 mouths to match up with every stick. An angle for every side, yes? That's why the side exists, is because the angle's there to give it room to live. So if I have 5 sides, I must have had 5 angles. So I would take 540 divided by 5, which comes out to be 108. Kick ass. 5 into 5 is 1, 5 into 40 is 08. Bam. So if I had an n-gon, can you come up with the formula for the degree measure of each interior angle? An interior angle is these angles we talked about here. So eventually there's going to be an exterior angle to talk about. A formula for the degree measure of each interior angle. You're like, I don't know, man. I'm not a math person. Yes, you are. We basically just did it. It's always going to be the total number of degrees I have to play with, which we already know is what formula gives me the total number of degrees. N minus 2 times 180. And then I'm going to divide that by n. Now again, if I just gave you that formula and said throw shit in, you would have no connection to it. But I'm hoping every step we took makes sense. Formulas have a hard job. They're supposed to capture every possible thing that could happen. So that's why they often don't look the way a simple problem would look, because they have to capture everything. Okay. I'm not going to worry too much about simplifying this down. So let's look at something else about these things. Let me see. Do I have another? I do. Oh yeah, I can use this. There's also an idea of a central angle. So if I start at the center and then connect 2 adjacent vertices with that, that's a little slice of this weirdly shaped pie, yes? And the angle that would be right there. Let me see. I should use well, it's okay. How many sides did this thing have again? I think this is our 12-sided one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Yes, okay. Remind me, how many total degrees if I just go around here? What's a total? So do you see how I can make triangles all around this thing? Basically cutting slices of the pie. Well, what do they all have to add up to be here in the middle? If I go all the way around, it's got to be obviously 360. So how do I figure out how big one of these is? How many slices can I make? 12. Because do you see how every slice gets a side here? And there's 12 sides, yeah? So I can make 12 of these slices if I just keep going around. I can make 12 of these slices. Pretend like I connected that right. I need this to just make, maybe part of this is just because it's too easy. I don't know. If it isn't too easy, I'm sorry. If I have 12 of those and they make 360 in the middle, each one of those has to be 360 divided by 12. Cool. Okay. So in general, so for this would be 30 degrees each. And why does it kind of make sense visually? What does it look like I just made? What angle here total with 3 triangles? Looks like I made a 90. Sure enough, 3 times 30 is 90. So, I mean, visually that kind of checks. So what if I just had a straight up just an n-gon? How big is each central regular, by the way? Regular n-gon. Each central angle would be what? 360 divided by n, because each side sets up its own triangle. I love it. By the way, don't forget, I'm not going to make you memorize these formulas. I would give them to you. You just have to be able to use them correctly. Yep. Oh, cool. And then there's one last thing. Of course there is. Let me see. So if I've got my, let me see if I can make this on my own. Oh crap. Pretend like this is a regular pentagon or 5-gon. I've got the idea of my center angle. Yes, I've got the idea of my, what we call interior angle. And then I've got something a little bit interesting. Let me make a bigger one. Let me see if I can do this. This should be exciting. Oh crap. That's sort of, all right, let me try it. You can do it, Jeff. All right, we're gonna work with this. Okay, everybody use your imagination. So I've got central, based on the center going out. I've got interior, just meaning these, the normal ones like we would think for a rectangle are 90 degrees each, the interior ones. And then I have an exterior angle. And that would be, if I take any side and I just continue, that's the angle it makes here. I'm gonna call it A. Maybe we can call it E for exterior. Okay, let me see. If there was a building that was shaped like this, and I'm a security guard at this building, and I have to walk the perimeter of this, am I actually going to walk right along the edge of a wall? Couldn't I instead kind of do a circle? I want you to, all right. Do you see how many exterior angles I have? Well, I have quite a few. Because every line I could just extend off forever, yes? Each exterior angle, does anybody disagree that every exterior angle you draw is the same exact size? They have to be, because this is supposed to be a regular pentagon, right? I want you really with me on this. If it's a regular pentagon, everything's congruent, that means every time I'm at a vertex, it's exactly the same image. If I just rotate it, it would eventually match up with itself, yes? So there's no side I could draw that it would be different out here, because it's all the same. So every exterior angle has the same measure. So if I consider an exterior angle to just be coming from the same direction, so here's another one, here's another one, here's another one, and here's another one. If I start walking, like right here, if I start walking, this tells me how much to turn so that I keep walking this way. This tells me how much to turn so I keep walking. This tells me how much to turn. This tells me how much to turn. This tells me how much to turn. So how many total degrees did I just go through? So all of the exterior angles have to add up to be 360. Because if I just follow what they say, I will end up going in a circle. So all exterior angles add to 360. So how big is each angle then? How big is each exterior angle then? How many turns did I have to do? 5, yes, based on how many sides. Isn't this the exact same formula for a central angle? You can do it, Jeff. Exterior angle measure, which also equals central, not central. Yes, central angle. Measure. So the central angle measure is exact same as the exterior angle measure. Okay. How many of you guys are like, well, this is more than I ever wanted to know about any of these, Joe? I know that stop signs, and that's all I gotta know, man. Leave me alone. Well, that's not true. Too bad. So let me show you here. Yeah, let me see if I can isolate this dude. That's all right. So coming back to tessellation, so that's those formulas for central angle, exterior angle, and central, exterior, and interior. I will give you those formulas. Yes, based on n. You just have to remember what n is. Coming back to tessellations for a moment. The tessellation that this one was composed of is that a regular foregon. Hell, is it even one of our standard shapes? Just look at any of those. But do you guys see how it's the repeated? Now, real quick. Do you guys see if I take this and I rotate it, and I rotate it, and I rotate it, any three-sided triangle or four-sided quadrilateral, any triangle or quadrilateral, if you just rotate, you will make a tessellation. That's nice. Because one really good question is, what's got to be true about my shape for it to work? Because I already know that triangles don't work. Sorry. Circles don't work, but triangles work and quadrilaterals work. Okay, I like it. This one's kind of nifty. Nice little T going on. This one, of course, is basically at the heart of all the other ones we saw. And yes, it's a little flower. Weehaw. Okay. Now, if I focus on tessellations created by regular polygons. So if I wanted to make a tessellation, Jeff, out of regular foregons, and if I use regular polygons to make my tessellation, this results in a regular tessellation. Isn't that crazy? Oh, math people. We are crazy. So a regular tessellation is a tessellation composed of regular polygons. So if I wanted a repeated, what is a regular foregon, by the way? What is it also known as? Square. I love it. So one way I could do that is just like this, yes? Couldn't I also offset them like we see with brick walls? I know brick walls are normally rectangular, but couldn't I offset these a little bit so that maybe I have it like this? Wouldn't that still work eventually if I just kept going? Okay. So if I look at this type, not that type, I want to look at the type of tessellation where they're perfectly lined up, down, left, right. Yes? Do you see where all four, I have like a central place where four squares come together? It's like right here. So the official name of this tessellation is the 4-4-4-4 tessellation. Because four-sided figures come together at that one point. Isn't that silly? if I want to do like we were doing earlier, and I create one out of triangles like this, and let me see if I can keep going. Let's see if I can do this. Yes, you can, Jeff. Look at you go. All right, that's not bad for me. For me, that is really good. If you're trying to get into art school with this, they're not going to take you. Can you guys find a similar point that we just talked about with the squares? What's a similar point happening here? How many shapes, how many polygons come together at that point? 6. So right here. So we would call this a 3, 3, 3, 3, 3, 3 tessellation. Don't ask me why they did that. Could they just called it like 3 with a 6 somewhere, 3 to the 6 or something? I mean, yes, but this is what it is. Too bad. And then, well, here, just to save us from my horrible writing, I've got an image of this one. So these, of course, are what's? Hexagons, and they have how many sides?
6.
Holy shit. So what do you think I'm going to call this one? Yes, what is it? 6, 6, 6. Yes, okay. So they shouldn't be drawing a little pentagram. You're drawing this instead on the ground. Yeah, nice and evil. Quick history lesson. Do you guys know the actual number 616? Number of the beast? All right, look it up. Get out. Okay. Not too much left. There's one little thing we sort of already talked about. Can you guys remind me convex versus concave? So for example, is this a convex or a concave image? And one way to remind yourself, what was it based on? Does anyone remember what it's based on to see which one it is? The official way to tell? If I take 2 points that are inside the shape and I connect them with the line, can I do that without going outside of the shape for every possible point, pair of points? No. Does the shape cave in on itself? Do you guys see how this is a cave here? Yes? So one way to remember what concave versus convex, if it caves in on itself, that's concave. If it doesn't, that's convex. So this would be a concave shape. So let's talk about this from the perspective of polygons. What kind of polygon is this in terms of concavity or convexity? Convexity. What do you guys think? Is that concave or convex? Let me give us an alternate thing. Is that concave or convex? This guy's concave, it just caves in. I can see 2 points that connect and go outside. So what's this one? Convex, yeah. Convex, concave. So you can identify. So before we talked about in terms of angles, and then I kind of expanded it a bit, but now we can talk about it in terms of these polygons. So polygon can be concave, convex. Every regular polygon, what do you think? Every regular polygon, what do you think they are? Convex, yes. So if I draw a polygon and it's concave somehow, it's not, maybe a little careful. Well, I'll be a little careful. Most regular polygons are convex, especially the ones we've seen today. I'll say it like that. Okay, let's see. No, I don't care about that. One more example of a tessellation. What's on the back of you? Oh, that's right. I want to show you that too. Using non-regular polygons. Yes? Just to show you. Now, one thing about like hexagons and the like, one thing that students have trouble with is, well, one thing I think that would help students, let me say it like this, is to realize that there are natural processes that end up with these shapes. One that's really trippy is called columnar basalts. I'm not a geologist, so you have to excuse me. These are naturally occurring shapes. There's a whole lot of cool physics and geology behind it. Has anyone ever taken any geology ever? Has anyone ever talked about these? Has anyone ever actually seen these in real life? You have? Where?
Devil's Profile up in the Big Bear Mammoth area.
Oh, okay. Yeah, all right. I've been around there. I just didn't even know these were there. Dang it. Someday I'm going to see them. What shape do they seem to be made of? Hexagon. You would see this and think somebody machined this, but this is natural. And the physical processes that actually created these, very cool. They're very nifty. But if you show this, that kind of trips you out a little bit, because you consider hexagons, especially those kind of things, to be like little things we draw. They have nothing, but no. And obviously you have like honeycombs, yes? Bees making honeycombs. That has to do with conservation of energy and stability and structure and all that kind of stuff, right? So there's a lot of things in nature that actually that naturally take these shapes. And the physical processes behind them are really cool. Okay. Last thing I'll say for today. I think, yes. Blah, blah, blah. Yeah. The last thing. Yeah, here we go. Just a little side note. You guys know what a silo is? Anyone know what a silo is? Not the show. I haven't seen any of this show. If you're watching the show, I don't know if it's any good. But I grew up in Georgia. As a little boy, growing up in Georgia. So silos have cylindrical shapes. And like in Georgia, they're full of peanuts. Yes? Or pecans or something. Or pecans, if you want to say it weird. Very quickly. I love you guys so much. Why are they shaped like that? If I made a similar structure made with a square base, yes, it would hold less with the same amount of material. So if I use less material, I can hold more stuff if I make it a cylindrical shape. Obviously, this only works for stuff like peanuts and so forth that can kind of like fill places in. If I have to stack boxes, I'm not going to use a cylinder, yes? So like circles can't fill in a square area and squares can't fill in a circle area, right? They just don't jive. But if I have little things, seeds or whatever, yeah, I'm using a freaking cylindrical shape because then less material for more volume. Okay, that's sort of like the three-dimensional analog of filling a space, yes? Okay. Oh, I almost forgot. Here's the practice test. So I'll have the answer key for it next time. This is our first real test coming up. So the next time we meet, this Thursday, this Wednesday's Thursday, will just be reviewed. I'm not going to do anything new, unless I do it accidentally. Oh, okay. I always forget. All right, guys. I'll see you next time.